Take a moment to pause the video and read this full problem statement, including these parts here, A and B. I'm going to start talking here about part C. So to determine the probability that Mike is going to be dealt a club on the next card, we need to know two things: how many of the cards remain, and not only just the cards in the deck, but including the cards that are face down. And that is this value here. 41 cards remain unknown to Mike. And of those, how many of them could be a club? So of those unknown cards, there are 8 clubs somewhere, either already face down or in the deck. So to find the probability of a club, we're going to take those two values and divide them, and we get 8 over 41, or approximately 0.1951. For the next probability question that's asked with this particular problem, we're told Mike's going to be dealt 2 cards, and we're trying to find the probability that he is dealt 2 clubs in a row. These 2 cards are dealt without replacement, meaning that if he's dealt a club on the first card that he receives, then there will no longer be 8 clubs missing somewhere. There will instead be 7. And there will no longer be 41 cards altogether unknown. There will be 40. So it's changing the values of what we're looking at, but the fact that we're still going to find a probability is the same. So I've noted this a little bit differently here. I put probability of a club, then a club, to try to show that there's this change of or order to the events, and that we're not replacing those cards. I just want to be clear about that part. So that's why I have, first of all, the probability of getting a club is 8 out of 41. And because these probabilities, or these events rather, are independent, I'm going to multiply by the probability of getting a club on the second draw. So on the second one, again, remember, if we're assuming he's already got a club on the first one, we only have 7 clubs left. Also, there was already a card dealt from all of the different cards that were unknown. So now there's 40 cards remaining that are unknown. And when you divide those, or actually work out that whole probability there, you should get approximately 0.0341. Because that is such a small probability, actually less than 0.05, the probability that Mike will get a flush is very low. So in other words, looking at it in the big picture, in the context of the problem, he should not stay in the game.